Okay, so welcome again, everyone. So we are all the way up to lecture four. It's on the second week. We've learned a lot of things, and I know it can be overwhelming because of the amount of the sheer velocity of which at which we're creating new knowledge and understanding it and that sort of thing. And so today, for the purpose of inspiration, but also for the purpose of allowing you to understand how data can be transformed into a model, and that model can be transformed into a service that actually has some practical significance. I have a colleague and friend here, Vikas Rana, who is going to share some of his experiences and create in by virtue of a an example applicable to the banking industry, so that you can understand how to make a model from a data set and then host it and then actually consume it in a meaningful way, right? And all the things that go in between it, this process. Okay. So with that, Vikas, I'll let you say hello to the group. Um, I see that you're on. Maybe you can unmute yourself. Yeah.
Uh, hello all. Uh, so as said by Prahlad, I am a colleague of Prahlad, and we have been working on different projects, and which is based on purely on machine learning. So today I'll be demonstrating you about a practical project which we have implemented, and I'll showcase you how can we build a model and probably save that model and deploy it into an application.
Yep. And so there'll be a lot of principles that we will learn about in between, right? Thank you,
Yes.
Vikas. And some of these principles include um, containerization, right? Which you will learn about and we'll understand what a container is, right? And then virtual machines, which you kind of understand, but then in the context of what is known as managed services on the cloud for the purpose of maintaining a production version of your model for consumption. And the other and the final and most important thing that we learn about is called an API, or an application programming interface. Okay, so uh, remember, Vikas's overview is going to be more of a show and tell. Okay, so you won't be able to capture and follow along with everything that he's doing right away, but you're going to try to understand all the steps. And believe me, it took me several years through my career to be able to see this end-to-end kind of implementation, and you're getting to see that in a 30-minute session, right? So you're definitely very fortunate to be able to see this happen in front of you all at once, and hopefully it'll give you some inspiration, but also some understanding of how you can take data and make it into a model that can actually be used to serve as a business purpose, right? Okay, so with that said, and without further ado, um, I will ask that Vikas, you share your screen, and we can kind of get things going. Um, yeah, so let
I
me
guess
enable screen sharing. Yeah, one second. Yeah, now you should be able to see. We should be able to see your screen. Yeah. Okay.
so let me know you're able to see my screen.
Yes, yes, we can. Yeah. And so, just another caveat, right? So, in your Google Drive folders, right? A version of this IPYNB that was being reviewed has been placed along with the associated data set. We will understand every single line in this and understand what's going on and the libraries that have been used and that sort of thing when after this demonstration of everything. But just FYI, right? Anything that you're interested in from here, including its artifacts, can be shared, and the recording will be made available as well. Okay. All right, Vikas.
Yeah. So to start with, we today we have so we want to build a machine learning model on a loan prediction. Basically, loan prediction is a kind of uh, you know is an wait a second. There's something. Yeah. So basically, what happens is whenever we try to deal with home loans, we try to take loan for our housing purpose. And today we're gonna develop a machine learning model which will tell you whether you are eligible for a loan or not. Okay, so these details which we have is like the gender, the marital status, the education, the income we have, and what is the loan amount. So to start with, first of all, as you see here, we will basically import these libraries, the machine learning, all the machine learning libraries we have, like NumPy, Pandas, Matplot, and some Matplot for visualization and Pandas for any data analysis. So we do have a train set with us, which is in this folder, which is
It's
tested
also
with.
available on your shared drive for in the
Yeah,
L4-7/16/2021 folder that I put up for you guys. Yeah. So you'll
yeah,
see two files there. Yeah. Go ahead.
yeah. So, so in the first step, we will load this data. We will load this data into a data frame. So here there is a command pd.read_csv and the path to the data set where we have loaded all the attributes of the data with the loan status. So you see the loan ID, the gender, whether it's married or not, the education, and apparently the income. So all these things are loaded here. Now we see a loan status here, which is our response period. So for any machine learning project, we have some predictors and the response variable. So we want to predict this loan status, whether it's a yes or whether it's a no. So yes means that you are eligible for a loan, and no means you are not eligible for a loan. And these are all the predictors we call it for this data set. So these are part of some data pre-processing step which we do before building a machine learning model. So I do df.describe. Df is my data frame, and I'm just searching the whether what is the maximum, mean, and the standard deviation. So these are some statistical values which we just do for any analysis for any particular data set. Now after that,
And let's pause there for 1 second because I'll just kind of highlight some key things. So you notice that there are numerical and categorical variables in this data set, right? And because if this notebook is running, could we just create a cell and just say df.info here for a second? Just so that we can have a look at, oh, you have it.
so we
Okay.
have
So great. So we have a bunch of columns. Several of them are categorical, some are numerical, right? So it says applicant's income is an integer, co-applicant's income is float, so there's some discrepancy there. We might want to standardize, but loan status is an object or categorical variable. Property area happens to be an object, which I'm not really sure if that's categorical or continuous, but property area could be a numerical variable, right? Loan ID is an object, that's because it's categorical, and so on and so forth, right? So one of the first things that you want to understand is, okay, what are the numerical variables in my data set and what are the categorical variables in my data set? And is the thing that I want to predict numerical or categorical, correct? Okay. And sometimes we want, I'm not sure if in this particular workflow we are casting the data types, right, because, but in a formal example, right, we may want to change the categories of certain columns into categorical or numerical or consistent float type. And for example, if float 64 is too much bit depth in order to store a certain number, we might relax that into something lighter and so on, right? Things that we've talked about previously in this class. Alok, you have a question?
Yeah, I noticed that you used a train test split, and I kind of wanted to know what influenced your decision to A, use it, and B, use it over something like five-fold cross-validation.
Mm-hmm. Vikas, would you like to answer that question and I'll supplement it?
I actually didn't quite hear the question.
Oh, yeah, I'll take it then. It's no problem. So basically, Alok's question was, why do we have our data set in two pieces, right? A training test set and a testing set, right?
Yeah.
So I mean, I'll answer this question. So basically,
okay, I can take that also.
okay, sure. Yeah, go ahead. Mm-hmm.
So I mean, so in any machine learning project, we do have a train and test. So here we do have two different training tests, separately data sets. In the train set, we try to build a model. Okay, we try to train that model using that particular data set, and we try to validate that model in our test set. So let's say we got some accuracy in our train set. Let's say it's some 80% accuracy, but now we want to validate that model. And to validate that model, we need to test that model in a very unseen data. So in our case, this unseen data is test set, so that we can get how the model is performing on any unseen data, and how the model is what is the accuracy of the model in the test data. So that's how we choose to do a train test split, and basically validate our model. So
Right.
that's how.
Yeah, thank you, because that makes sense. And and to draw distinction to cross validation, right? During the last lecture, it so happens I was explaining how we can do leave one out cross validation, and also five-fold or 10-fold cross validation, basically K-fold cross validation in general. But Alok, to remind you on the fact that some of the facts about cross validation. Cross validation is not your go-to for building a model. It is more of a strategy to work out whether your model has been overfit to a certain type of data, which is a subset of your data set, or if there is a great amount of sensitivity, uh, uh, to the choice of data that's used to build the model, right? So if learning from a piece of your data leads to a more powerful model for determining the response in a very special data set, portion of your validation data, and learning from another piece of your data leads to a very diminished performance in another outer sample cohort, that's not good. That means the choice of data is what's making your model better or worse, but in general, you want to make sure your model is going to be broadly applicable to all sorts of similar data, right? So splitting the data into training and testing helps you make sure that you have at least one piece of data that you've never exposed to the model, basically, which you can use as an unbiased validation cohort, so to speak, right? Cross validation is generally going to be limited to your training set, so that you can know if the model that has been built without knowledge of the test set has any likelihood of being overfit. And so you make your best guess and say, put your best foot forward, identify whether your model is prone to overfitting, then choose an appropriate cohort along with some features that are engineered, drop unnecessary features, etc., and make a model. And then after that, once you're done with the phase of establishing whether your model is likely to be overfit or biased or whatever, and you're happy with what you've got, then you apply it to the test set to see if the test performance mimics or is at least close to the training performance. And if they are similar, then you have an additional validation about the fact that the model is likely not only great at answering the questions at the back of the book, but answering general questions, so to speak. Right? Okay. So go ahead, Vikas. I'll let you go on with your thoughts.
Yeah. So once we have after doing df.info, we find out what are the categorical values and what are the integer or float values, and these are some of the data types. Now after that we check. So so there is a lot of data pre-processing steps we do before making into a model ready data set. So here if you see, I'm just finding out how many are the null values here in the data set. So I'm just doing df.snull.sum function, which will determine how many null values are there in this data set. So if you see, there could be many null values here. So these are some filled values, but let's say we have some nan values over our data set, and we need to check how many null values are there. So this is the way how we do that.
And sometimes these null values might be discarded. That means you'll say, hey, if any row has any column with a missing quantity, let's delete that row, right? You can do that. Or you could say, hey, I don't want to delete my records because I only have a little bit of data anyway. And you could do something called imputation. Imputation is the process of filling up or guessing at what the missing data is for the purpose of working out what.
And which we are doing in the next step. So we are imputing some values with the mean value of that particular variable. So if you see the loan amount, there are 22 null values are there. So we are imputing these null values with the mean of the data set, the mean of the particular column, which is loan amount. Yeah.
So basically, if there's a loan value that's missing, we're saying, hey, in the interest of not ditching that row for lack of data, we're going to fill it up with the mean value of that column so that it has some value in there. right? It may not be the most sensible thing in the world, but sometimes it is, right?
Sometimes we do, yeah.
Yeah.
And that depends upon how many missing values are there. So let's say we have less than 5% missing values. So we can go for a mean imputation. But let's say we have a lot of missing values, then probably we have to find such any way which is possible enough to do some kind of missing value imputation.
So
So once
in
we have,
an example, this brings up an example that Vikas and I worked on. So there was this one project about vital signatures, right? And so we had a patient, and the patient is giving us their heart rate and their blood pressure and their respiratory rate and a few other vital signs, right? And sometimes the sensors that are collecting this data are loose or they're not working out right. And a record that we receive might have missing values. But in that case, instead of mean imputation, we used the last value that we knew, the last known value, as the strategy for filling up the missing values. So if I knew that the heart rate was 80 beats a minute at time point t equal to 1, and then at time point t equal to 2 it was missing, and then at time point t equal to 3 it was 82 or whatever, the one approach is to fill the missing time point 2 value with time point 1's value, right? Because that's the last known value, and so on, right?
yeah,
You could also do the average of the values, which is a fairly good fit, meaningful thing to do in this particular example. But there are lots of different strategies for imputation. This is one of them, right?
yeah. And we basically do forward fill for that. So there is a function called forward fill. So like this, you see mean is there, mode is there. So these are some statistical, figures. But in our use case which Prahlad has just described, we have used forward fill. So which will take the last value and impute with the last value of any particular patient. So once we impute that, you see there are no null values. We see that yes, there are no null values now, and we can proceed with our next step, which is basically EDA. So
So
EDA here, yeah,
exploratory data analysis, right? Yeah. Mhm.
yeah. So in EDA, we just since it's a analysis, we kind of do. So there are a lot of analysis which we do in EDA, which can be univariate analysis, bivariate analysis, and also. So here we're just counting on how many in this particular data set we have. In this particular data set, we have how many. What is the count of male and female? I mean, the count of genders. So in our case, we have only two genders, which are male and female. Okay. And like that, we have calculated the count. This is a count plot here, and we are using SNS. SNS is basically a library which is used for visualization.
The third line, yep.
The third line, CPOM.
So far we haven't really been doing plots in Python, but today when we finish Vikas's portions, we will you will have a chance to explore Seaborn and so on by virtue of this notebook, right?
Yeah.
But
Yeah.
exploratory data analysis is very important to be done before you dive into a problem of machine learning, only so that you know that the data set makes sense. And sometimes you know that there are certain inherent biases in the data, right? For example, this data set is more biased towards married people because you have more participants who happen to be married, right? And you should be saying okay with that. You should be okay with this, if and as long as the status of marriage doesn't seem to be terribly important in your modeling problem, or you would proceed with. Otherwise, as a data in terms of the data collection effort, you would say, hey, let's try to find some more unmarried people to add to our cohort, or let's do something called data generation, right? Or pseudo data creation for the purpose of filling up data sets that correspond to the less represented class. Yeah. Okay.
Yep.
Yeah. Go ahead.
So like this, we're just doing a count of some particular attribute here, which is dependent. Like that, we have just checking. I mean, what is the count of graduates and not graduates here in the data set. So likewise, we have done for so many attributes. So many columns. You see a self-employed and property area like that. So we can see that the semi-urban areas are the one which are having going for the which are maximum count among urban, rural, and semi-urban. and we see in this data set that the count of loan status. So loan status is a response variable, which I just mentioned before. So you see that the count of yes, I mean the count of people uh, accepting the loan is around yes. I mean the count is around 400 plus, and the count for no is low. So this all can be demonstrated using this data in a process which we call it as EDA.
So now let's pause here and do a little fact check, right? You
Yeah.
see here that your two classes in your response are imbalanced. You see, there's a class imbalance here. You're trying to predict whether a loan will be denied or approved, but in your data set, you have many more people who've gotten approved than you've got them being denied, correct? So, honestly, let's say, I'm just making this up because I don't have the actual numbers here, but let's say 2/3 of the loans are accepted, right? And if I made a model that basically said that every loan is accepted, then I would still be right 66% of the time, correct? You see my point? So suppose I had 100 loans, and in reality, in my data set, 66 of them have been accepted. And I made a rule in a machine learning model that said, predict every loan as accepted, right? Then I would be right 66% of the time, correct? So imbalance of classes is sometimes a detriment, right? Because you might learn that it's okay to say yes to everything. It's like a child at home, right? If basically, if at the end of a class, if I say, did you understand? And he says yes, he knows he can go home. Then he's always going to say yes, even if he means to say no, right? You know what I mean? And so from that perspective, a machine learning model is going to be prone to biases based on the kind of data that it's fed, okay? Which is always a good idea to deal with upfront. But today we're not going to deal with that sort of thing. I'm just saying, it is something that one must keep in mind, right? So as to not lead to an answer where, you have all your answers in a certain bucket, right? Now, let me ask you another quick question here, okay? So last time we learned about classification and regression, right? If our response variable, that's the y variable that we want to predict, is categorical and it has yes and no, would we be doing classification or would we be doing regression? Anyone?
Yes.
Sorry? I couldn't hear you.
If the y value is categorical, then you would do a classification.
Classification, that's correct. Yeah. So in this particular case, we're making a classification model. And since there are two possible classes, you have binary classification. Okay. Okay. Go ahead, Vikas.
Yeah. So the next thing which we do is finding out. So there are different types of visualization techniques which we do in our EDA process. So before we were doing a count plot, this time we're doing a test plot. So this is just we're plotting the applicant income, which is in the x-axis, and how many people are there, which is making such plots. In this case, see so this process is basically something where we plot it, and you see there is a normal distribution coming on, isn't it, Prahlad? Yeah.
So yeah, so basically, let me just quickly give you some preface to this. So in this particular distribution, you have a heavy tail to the right, correct? That means you have, most of your applicants have a loan between 0 and let's say 100,000. Is that or 20? Loan between 0 and maybe 10 or 15,000, right? And after that, there are some people who have really high value loans up to 80,000, but that's not the majority of the people. So this is an example of a right skewed distribution, correct? As opposed to a typical normal distribution, yes, where you have as many people. I mean, the likelihood of finding a loan amount to the left or to the right of the mean is about the same, right? Here you're more likely to find a low loan amount from this data set, whereas you will find data, corresponding to very high loan amounts as well, right? So because there's not that much data associated with the very high loan amounts, maybe this model may not be very good at dealing with high loan amount decisions, right? Because it may find that we may find in this data set that the high loan amounts are all rejected. Does that mean that all high loan amounts are supposed to be rejected? Probably not, right? So identifying biases in your data can be done for continuous variables like this as well. You see?
Yeah.
In addition to the categorical variables. So categorical variables are analyzed, let's say, from the standpoint of, frequency distributions or bar plots and so on, like we saw previously. And then continuous variables are analyzed for the purpose using the idea of distributions or histograms and so on. Okay, and in this case, you're looking at something called a kernel probability density plot, where the y-axis is the probability of finding a loan amount in this example that is any specific value along the x-axis. And the x-axis are all the different possible loan amounts, right? And you can see that most of the loan amounts are between 100 and 200 in this particular case, right? I think I'm not really sure what the units of this thing is. Maybe it's 100,000 to 200,000, somewhere there, right? So it's between 100 and 200,000. You have a peak, which means the most likely loan amount is in that range. So we're probably going to be good at estimating that kind of loan. But as we get into the higher tail loan amounts like 400 and 500 and 600 and 700 and higher, we're probably not going to have a lot of data to kind of make a decent rule, right? So the exploratory data analysis tells us something about what our model might be good at and what it may not be, or what we should trust it about and what we should not trust it about, right? Does everybody follow? Okay, let's go.
Yeah. So as you see, I mean, as Praz explained, that the most of the people are going for a loan amount which is between 100 to 200, and as the loan amount increases, there are very few people. I mean, very few people which are having loan amount which is greater than 500 or 600. Right. So this just tells you about the data how we plot it. Now in the next section, we are doing some feature engineering here. So if you see, we have, I mean, if you see, we don't have any total income as an attribute in our previous data. You see, let's go to previous data. We don't have that column as such. Now we want to create a column which is called total income from the existing columns which we have.
And so the process of creating new columns based on other columns or based on some formulaic approach, right, in general is called feature engineering, right? Yeah, and we also call it in general mutation. So we're taking a data set and we're mutating it to create new columns that provide some new information, right, based on a combination of columns or based on a formula or something like that.
Yeah.
So these are just some more exploratory analyses. Yeah.
And now this is a heat map. We call it as a heat map, which will tell you what is the relation between attributes with each other. So there is the x-axis, you see all these attributes are there: the applicant income, the loan amount, credit history, total income, which we have just created, and these are finding a relationship between their existing attributes, like applicant income, co-applicant income, total amount. And
so
these
it's
numbers
correlation plot or a correlogram or some, you could call it one of many things, but it tells you the amount of correlation between every field and the next. Now, the reason why we look at something like this is ideally every attribute will be uncorrelated with the next, right?
Yeah.
Let me explain why. So suppose I knew that the heights of students in my class is related to the likelihood that they will fit in the door, right? Okay. Won't height plus 5 also tell me the same answer? Yes, right? Wouldn't height times 2 tell me the same answer? Yes, right? Any mathematical function of height is going to tell me about the same response in the same exact way. So if I had two attributes that are telling me the same story about the response variable, it doesn't make sense to include both of them. It makes sense to include one or the other, right? And so looking at correlations is important because we actually want the correlations to be very small, right? between variables that are selected for the modeling process. Because if they're highly correlated, like total income and applicant income, it says the correlation is 89%, probably we should consider one or the other. You see my point? Now, we can consider all of them, but the risk of having highly correlated variables is that we potentially, right, potentially will end up with a model that will be incorrect in terms of its logical relationships with the response. And we have seen this happen before, right? In the British seatbelt study in the last class, right? And so correlations are a good way to make sure that you don't end up with something called variance inflation. Okay, variance inflation. So variance inflation is an issue where you have variables that are pretty much telling you the same story, and you're including many of them, and because of that, you end up messing up the model's ability to learn from the meaningful attributes, right, and their relationship to the response. So you want to get rid of variance inflation. Yeah. Yeah. Go ahead, Vikas. Yeah. Mm-hmm.
Yeah. So we have done all the analysis and all the EDA process we have done. Now we're just going for building a model, and before building a model, we're just drawing some unnecessary columns, like dropping some unnecessary columns which are not required. So in our case, if you see, there are a lot of unnecessary columns. So we are taking only applicant income, co-applicant income, loan amount term, in this case, total income, loan ID, and the co-applicant income, right? And now, if you see, this is the process of we are doing a label encoding, where we have these columns as categorical columns, but the model will not understand these as categorical columns. We have to convert into some integers or some encoders such that the model can understand it as zeros and ones. Mm-hmm. For that, we use, when we have this SQL library, SQL processing, we import label encoders. So if you see,
so label encoders are basically trying to encode a categorical value in terms of some numerical label, right? So suppose male and female are two possible values of a categorical column. I might make male as 0 and female as 1, or female as 0 and male as 1, and so on. Generally speaking, the label encoder is going to go in alphabetical order of all the different categorical levels that you have in a column, and then give them a number assignment. Okay. Now, there are two reasons why people do this. Number one, there are certain models in sklearn that are requiring this, right? They require your labels to be encoded. But in other examples, if a bank had personal information here, right, and you wanted a data scientist to develop models from that data, you probably want to encode the labels so that their privacy is protected, right? The data of the privacy of the people whose data we have here is protected, and said data scientist doesn't actually know who these people are. You see my point? Okay. And so label encoding has an ethical purpose, but it also has a technical purpose in this particular case, for the purpose of enabling the use of a very specific modeling approach, right?
Yeah. So you see, we have done some label encoding, and all those in the gender columns, you see, earlier we had male and female, but now we have all these label encoders. For married, we have yes and no. So maybe yes is no is corresponding to 0, and yes is corresponding to 1. And like that, we have for all the respective columns we have in a data set. So now we actually try to build a model, and for that, we kind of pop the loan status, which is a response variable from the existing column we have. So you see, we try to take these predictors into X variable. Okay, so these are the X, the X variable we have. We have all the columns which are predictors, and Y, which is basically the loan status, which we are defining or which we are predicting via model.
Correct. So we're splitting out the X's and the Y's, right? So just like we did in the last class, is basically taking out the predictors and the predicted response column, correct? And making them two separate variables for the purpose of our next step. Okay, go ahead. 34.
And next, we are just doing a train test split where, so in the train data set, we have lot many rows, but now we want to do a train test split so that we can validate our model on a test set. So here we're just doing sex train, X test, Y train, and Y test. And we are using train test split as a function, which includes X, which are our predictors, and Y, which is our response variable, into a test size of 25%. So let's say we have data and we are just taking out 25% for our test data set, where our model will be validated. And once this is done, we will go for our model training process. So this is basically what we are doing as cross validation. And we are doing it as five-fold cross validation here.
Okay, so let's pause here. This is very important, right? At this point, we have only been working with our actual training CSV file, right? And we split the training CSV file into another set of train and test, right?
Yeah. Yeah.
So we have two bags of chips, right? One is a training test and set and the testing set. We're just taking the training set and splitting that bag of chips into two bowls, right? And we're calling that train and test. And then doing cross-validation again in that same bag of chips. We, at this whole point, we have not touched the second bag of chips at all, right? We're ready to build everything that we have to build using just the training set. And all of these are techniques in making sure said training set is appropriate for building a model, and this model is not sensitive to variations in the training set, assuming that this training set is truly representative of the population of data that that training set represents, and that the test set is going to be similar in terms of what it represents as a training set, right? Okay. So go ahead, Vikas. So at this point, you're just building the models and you're basically making a classification model, right? So what we see here is a function, right? So you see that def classify. So what we have here is a very custom function that prepares takes a given model, right? Takes a given data set and then makes a model, right? And it reports on cross-validation accuracies, much like what we did in the last class, except this is doing it for a very specific train test split by splitting the data in various different ways, right?
Yeah.
Okay.
So importing some classification models like logistic regression and just creating an object of that logistic regression and passing that object into this classify custom train function. And we get that accuracy is 76%, 77%, sorry. And the cross validation score is 80.9.
Now, again, here, this is overall accuracy, right? And the last class, we talked about sensitivity and specificity and precision and so on. And I'll show you some slides about, all these metrics, today as well. But, overall accuracy can be biased. Remember, if your data set is, unbalanced, right? Overall accuracy could be very misleading, correct? And so that's why you want to find accuracy within a given class and within the other class of your response separately. And that's where you come up with sensitivity and specificity that we briefly talked about last time. But yeah, so at this point, we're just looking at this high level stat of accuracy and fitting various models, right? Logistic regression, decision trees, and random forests, which are like collections of decision trees. Extra trees, which is another collection of decision trees, and so on, right?
And out of these, we just find out that the random forest classifier is doing best. So this is the final model, which we will just convert into a pixel file, because this is how we are, this is which is performing best in terms of all the other models we have.
Mm-hmm. And again, now when we say performing the best over here, we're looking at overall accuracy as the metric, but there could be lots of other metrics. So, but for today's class, we're saying, hey, this accuracy is our metric, right? And we're going to assume that it's sufficient, right, for the purpose of moving forward. In a realistic scenario, we might look into lots of other characteristics, right?
So once we find the best model, we try to save that model as a pickle file. So pickle is basically a pickle file is something which is a binary file, so that we can store the checkpoints of that model, and we can load that model again in our API. So for that, we're using Pickle. I mean, Pickle is a library which we use, and we just pickle.dump the model, which we have just created, to the file path. So this is our file path basically, and we are saving this model. So this saved model is stored in my, here, you see, model.pkl. And now we're going to try to consume this model into an API so that that model can be exposed as a service later. Yeah.
Mhm. Okay, so at this point, we break away from the Jupyter notebook, right? And then we need to be able to consume this model. So last class, what did we learn? We learned that we could take this model and create a Streamlit app out of it, right? So that we can test it against new outputs. Now, and that's one way of doing things, right? But another way of doing things is to take this model and convert it into something called an application programming interface, which is like a hosted service which can be accessed using something called a RESTful HTTP interface. That means by means of a web URL, right? Passing it the inputs that it needs, and it responds back with a prediction, right? And as such, the next part of this illustration is going to be to take this thing, make an API out of it, right? And then host it for consumption and testing. Okay. So with that, but before we go to that, let's see if there are any questions from the group. So number one, right, the notebook that we're looking at right now is uploaded on your Google Drive, right, for everybody's reference again. But that notebook has local file paths and so on, which you'll have to change into your relevant file paths as per your Google Colab environment if you're running it there, or if you're running it locally, just as a caveat. But any questions thus far in terms of our model building endeavor? All of it should seem mostly familiar, except we've used a few different libraries, understood a few more things like imputation and some aspects of exploratory data analysis, right? Which help us logically infer the scope of applicability of our model and the sensibility of our data set, right? No questions? Okay. Okay, Vikas, so let's kind of look into the API process, right? So we have a script that helps you do that. And I will share the script as well.
So this is a script for, and we are using Spider here. Spider is another IDE. So before that, we have used Jupyter Notebook for building a model. Now for API, we are using another IDE, which is Spider. And this is something we will use in a API. In another 5 to 10 minutes, I'll demonstrate how we can use this API as a service and load this model, and probably I'll teach you how we can build a RESTful endpoint. Okay.
And so why choose Spider as opposed to a Jupyter Notebook? In this particular case, we're looking at a script which has a file path, file extension .py, right? As opposed to .ipynb. And Spider is an environment that's more like RStudio, right? That we've used for R. And so this is kind of like equivalent to a .r script, correct? So it's a more suitable environment for the purpose of engineering .py files. Okay. Yeah. Go ahead, Vikas.
So yeah, we are just loading the same libraries. And to build an API, we use Flask as this is an important library which is used for building web applications, but as well as we are using it for building an API out of. So this is just an important library to keep in mind too, so that we can build an API out of it.
Right. So Flask. So Flask is the app is a library that we can use to make APIs and web apps, etc. Right.
Yeah.
Mm-hmm.
So now here we see that. So to run an application, we use app equal to Flask. Let's go name it. So it is just starting an application, and inside it we see that we are loading the model here using pickle.load. So previously we have used pickle.dump to basically save that model, and now we want to load that model using pickle.load, so that this model will automatically load it into this loaded underscore model variable, and we can use this model anywhere in this script.
Mhm.
Yeah. Now we define the paths out of it. So you see this .r.root is basically a decorator here, where we define the paths. So the path is a lone hyphen prediction. So we will use this path, and it will be important for uh, planning this API into this particular path.
So
That
when you think about API, let me just quickly preface this a little bit, right? So API stands for application. We just mentioned this application programming interface, right? Now, this application programming interface is going to be some web hosted solution that will allow you to access this model that we created, correct? And so the API is going to be like this. We're going to take a request, send it to the API via a URL, request via URL, like a web URL that you would enter in your Google Chrome browser, right? But request via URL, which hits the API, and that comes back with a response. So this is the idea. You have a request goes to the API comes back with a response, right? And so in order to work out what response you will get, we are defining the API response as a function here. Okay. So the API response is going to be defined as a function called API underscore response in line 21. But in order for this function to be accessible by means of a web URL, we're saying it will be accessible at whatever URL that you have hosted your app at /lone-prediction. So if my IP address is 32.156.123.5023, I would say that, /lone-prediction would be the endpoint, right? Which I need to send some request to in order to get a response, right? So that's the way it's written out. The red text on line 20 is defining the route, right? That you would need to take in order to get access to that function by means of a URL. That's what it's doing. Okay. Following, everyone? Okay. You go ahead, Vikas.
So as mentioned by Prahlad, that we're using this function to, so this function will be used for loading our data. And here, if you see, we define request.getJSON. So this getJSON method will request a data, and that data will be requested by this request library, and it will be stored into a data frame, which is a variable called data. So for that, Prahlad, shall I demonstrate Postman also here? Because
Yeah. Let me quickly finish talking about this, and then yes. So basically, what this particular thing does is on line 23, it is reading in the information that you will pass in through the URL via means of the very specific endpoint, right? And it's interpreting that information in the format that it's expecting, correct? And then converting that into a pandas data frame, and then we're assigning that data frame specific columns that we're expecting to see, right? Based on the model, total income, applicant income, whatever else, correct? And then we are saving, once we have saved all this information together, we're giving some column names to it, performing the label encoding for the categorical columns the same way that we did in the training time. Yes. And then using the loaded model to make a prediction on that new data frame on line 40. And once you've made the prediction, you're basically simply taking that prediction, converting it into a string on which is a set of characters on number 41, and printing out a response based on what you see. That means if the response happens to be 1, that means the loan was sanctioned. Otherwise, the loan was declined. And so we're just creating some print statements or return statements, sorry, so that this function returns a result that in turn can be returned as a response from the API, right? And then the very last line is simply hosting this API at a certain port. And we're saying this app is going to be, this API is going to be available at your URL, right? Your URL for your computer, let's say, :8118, the port number, / that loan-prediction endpoint, right? So it's defining where this app will be available and accessible to the external world. right? So this is all that this thing does. It basically creates an application programming interface out of your model so that it knows to expect a certain kind of input and come back with a certain kind of output. And it expects the inputs to be in a certain order and so on. Otherwise, it's garbage in and garbage out, right? You give it something, nonsensical, it'll give you back something which will be either a 0 or 1, but it may not make a lot of sense, right? Okay. So the underpinning assumption of using APIs is that you know how the API works, because otherwise you're not going to be getting a sensible result out. Okay. Okay. So Vikas is going to be able to now take this API code, right, and then run the host the app API, right, and then we're going to test it in a second. And in order to test it, we're going to use this tool called Postman. Postman is a software you can download into your computer or use as a web application, which simply will access an API and allow you to send some information in and receive back its response. Okay. So with that, Vikas, I'll let you kind of move that forward.
Yeah. As Prahlad mentioned that, so once we get a response from a model, so if it is 1, we'll say loan is sanctioned, and if it is 0, we will say loan is declined. Now we're going to try to run this API now, which is hosted at 0.0.0.0, and the port number is 8118. So we can change this port also if you want, but for now let's keep it as 8118 / loan prediction. So I'll tell you how we can use it via Postman. First of all, we need to run this API, and for that I'll just click this button down. I'll just take time to go that model and finally the API endpoint.
So what we're doing is just simply running the Python script, which will in turn run line 51 really, and then host the API at this port, right?
Yeah.
And now we can access the API from this port, right? And in order to access the API from this port, Postman is going to help us do it, right? It's going to help us craft a good, well-formatted request to this API so that it knows how to respond. Okay?
Yeah.
So let's check it out. Okay, so we're going to get into the Postman application.
This is a Postman application we have.
And yeah, so in Post, basically you have there you go. Yep. So in the Post, you see the big bold letter saying Post, right? Over there, you're entering your URL and the endpoint. And then after that, underneath, you're going to enter the kind of payload that you want to send to that particular endpoint. So you're telling it's the loan ID, the gender, the status of marriage, dependence, education, all of that stuff that the model needs. And notice it's in a very specific format, right? It's like column ID column ID column value, and it's all inside these curly braces. That format is known as the JSON format.
Yeah.
Okay. And that was what the first line of our API response function was interpreting, right? Okay, so now that we know what payload to send it, right, we will simply send it, right? So there's a big blue button for us to send it. So we're going to send it. And there you go, right? So it came back with a response. So we sent a request, a sensible request that has been formatted in a nice way, and we came back with a response. Okay.
Yeah. So based on these attributes we find out that for this particular person, which is having a loan ID, and she's a female basically, and she's married. She is married, and she has no dependents. Her education is graduate, and she is not employed. Her applicant income, and the loan amount we have is around 1100, but I don't know what is this currency, but let's say we have some dollars here, and the loan term like that. We see based on these attributes, we see that the loan is declined. I mean, she can't access to the loan yet. Now, if I decrease the loan amount, let's say I decrease it to 11,110. Now let's see how the response we have. And you see, for this less low amount, the loan is sanctioned. This is how the API works. And when you change the attributes here, and based on any attribute or based on the model which we have predicted, so the model will take these attributes as an input and will give you an output for this particular use case, which is loan prediction, and it will give you whether it is a loan is sanctioned or whether or the loan is declined. Yeah.
Okay, so
So
now
now we're
another
gonna
quick thing, right, about 0.0.0.0. So when you run your API at 0.0.0.0, what happens is by default, that particular port is going to be accessible to the external IP address of your machine, right? So by hosting it at 0.0.0.0 colon 8.1.1.8, the external IP address of my machine, which is web accessible, right, if will be also exposing port 8.1.1.8, provided that port has been forwarded to my machine by means of my router, right? And so that's the networking aspect of things. But basically 0.0.0.0 ensures that the external IP of the machine, right, as exposed by your router, is now going to also have access to this port 8.1.1.8. Okay, that's the idea. Okay.
so we have successfully created an API. We have tested that API into this port and the path to that port. And now we're going to deploy it in a container as we speak.
So now that we know that this API works, right, and we made it run inside the Spider interface in order to get the code to work and expose the API at port 8.1.1.8 in this example at the endpoint loan dash prediction, we want to be able to deploy this API anywhere in the, on the internet, right? For access anywhere on the internet without having to make sure that this computer sitting here has Spider installed and has hosted the API, correct? We want to be able to, in an agnostic manner, get all the resources that this computer has, which this particular web API interface requires, put together in a single unified form, right? Which can be pushed into a server anywhere and then hosted, right? And the process of encapsulating the resourcing and the code together into a single form is what we're calling containerization. Okay, and we'll use this tool called Docker for doing this. And so Vikas is going to get into that step next. Yeah. Yeah.
So as Prahlad said, that now we have our API ready, and let's just go for the Docker now. So for Docker, we basically, so Docker is a platform as a service which will take all your application into a container and deploy anywhere in the internet, as mentioned before. So there are some terms and conditions for the Docker and some rules and regulations also. And for that, if you see, we have our API, which is loan-prediction.py and our model.pkl file. Okay. Apart from that, we have a Docker file here. So this is the file which is so important to create a Docker image. Now we're gonna deploy this application into a Docker image first, and then we want to check that Docker image, whether it is running or not. And to check that, we will again use a Postman as a tool to test our API. So let's just go to this Docker file, and yeah.
As much as Docker is complicated, it's also simple, right? There's one file called Docker file that you need to put into the same directory that you have your code in. Okay, that's the one file. And in
That's
that
the
one
one
file, you have some code, right? Which is telling you about the resourcing and libraries and whatever else that you need in order to get this code going. And that's what Vikas is going to go over for a moment, right? So let's just look at that Docker file, Vikas. So we're using this thing called Notepad++, which is highly recommended, okay, for the purpose of reviewing arbitrary files. And so what you see here, right, for example, we're saying from Python 3.7.6. That means there is some container that's available somewhere on the internet, okay? And that baseline container is Python 3.7.6. Is that correct, Vikas? And then we're customizing it from there, right? So we're saying, hey, let's not rebuild the wheel, right? Let's not remake the wheel. Let's start with something that works, And there happens to be a cloud repository for a Python 3.7.6 container, which runs Python already. And now we're going to customize this thing to be able to run our stuff. And to that extent, these lines of code do that. So we're creating an application called /app. We're putting some code in there, installing, an installer called pip, which is in line 5, and subsequently using this pip3 install requirements line in line 6 in order to install all the requirements that we've listed in this requirements.txt file that is also in the same folder. So if we can open requirements.txt, a second tab here, guys. There you go. So we need pandas, we need NumPy, we need scikit-learn, we need GCSFS. GCSFS is basically Google Cloud specific, right? You may not need it if you're not deploying this on Google Cloud, but we are. So we're using that. And then Flask for the API, datetime, and pickle for the purpose of installing, being able to kind of
Load
save
that model.
models and reload our models and so on, right? So go ahead, Vikas.
And all these libraries you see, this is already embedded to our API. So if you want to check which all libraries we want, you just want to go to your API. Okay. And let's just go to API. Let's see that, NumPy is installed, pandas is there, pickle we want. Okay, GCSFS as mentioned for deploying cloud. Flask is there, datetime is there, skiller. So to check which all libraries are required to deploy an API, we can just copy these libraries and just put it over here. Just to ensure that all these libraries are installed to our application, and we can probably run this Python script to deploy as a Docker image. Yeah.
Great. And so now we have a Docker file. And so the last few lines of that Docker file we hadn't gone through, but the last few lines of the Docker file are simply saying make the loan-prediction.py script, which is in line 7 there, executable. So chmod plus rwx is basically a Linux command to say make that script executable. And then it's saying run that script between line 8 and 9, right? It's saying run that script using Python and expose port 8118. In other words, do the port forwarding from your virtual machine to this to the external IP address of the machine, so that the external IP address is at port 8118 can access the API that you've hosted. So these are the instruction sets, right? Now in the industry, we call this DevOps, right? Basically, we're trying to operate, development operationalization, or what is, I use the word DevOps on a daily basis, and
For machine learning, we use MLOps.
MLOps, right? So DevOps is basically a set of practices that combine software development and IT operations. So development and operations, there we go, right? And now we, in this particular case, we're doing DevOps for machine learning, right? So it's called MLOps, right? Okay. And so this is the magic of DevOps, right? Basically, it's infrastructure as a code. We're taking code and allowing it to encapsulate all the infrastructure and software and everything else that's needed to run this code, our API, in one single place. Okay. And I know there's a lot of things that it's not meant for you to memorize. It's basically for you to understand the experience, and then we'll go through it step by step, later on as well. Okay. So yeah, go ahead, Vikas. So now that we have the Docker file, we have the requirements file, and we have the .py file, and the model pickle file, all of these things are put together, and now we can use some Docker commands for the purpose of building the container itself, right?
Yeah.
Okay, and so
yeah. So just to build our or to deploy our API into a Docker container, we just need these 4 files here. So the model which is required in our API, this is our API, loan-prediction, a Docker file which we have just discussed. I mean, the series of commands to deploy an application, and the series of and requirement.txt, which will have all the necessary libraries to be installed to our application. So this application is basically an API here. So now we're gonna take all of these 4 and create a Docker image out of it. Now let's go to our Windows PowerShell here. So that's the terminal where we'll first go to our working directory, which is, let's just loan prediction.
So these are just simply commands that are being entered on the PowerShell in Windows. Now it's similar to the Linux commands that you might enter in a Linux machine, but what Vikas is doing here is he's using a Windows machine at the moment, so he's trying to do it on his machine, right? Yeah.
Yeah. So now once we have come up on a working directory, we will use this command, docker build -t loan-demo and all. So I'll tell you what is this. So build command is used to build a Docker image. -t is tagging your the name of the image, which is loan-demo. So now you can, we can just change it to some other name also, any random name you want. But now we are doing loan prediction. So let's say loan prediction space dot. So dot is taking all your files in a working directory, and so these are the files in a working directory here, Docker file, prediction, model PQ collect, and using those files, it is building a Docker image out of it. So now I'll hit it and hit enter for it. I will see how it builds a Docker image.
So there we go. So now this is going to take a few minutes, right? Because we'll take, yeah, so it might, because it's going to have to download the starting container and then customize it and so on. In this particular case, it may have thrown an error. Oh, it looks like there's a hidden file there, Vikas. So maybe just copy just the files you need into another directory. And it's looking for that hidden file, the dot prediction pptx that you have open, and it's not able to do that. Just make a copy in a subdirectory and it should work from there. Yeah.
Let's just close this thing first.
You might have changed close the PowerPoint as well.
Yeah.
All the files if you want to do it from the same directory. But basically only those 4 files were required, right? And so it's trying to make sure that no other process is holding on to those files, and then it's getting in here. So let's try that again.
So you may encounter these errors before building a Docker image. So they've tried it a lot of times before also. And sometimes it happens that we get some errors.
There we go. See?
There you go. Yeah.
So it's executing each line of that instruction set in the Docker file, right?
Yeah.
That's what's going on here. And then it's building this container. This container is going to be like this large file of sorts, right? And then that container is something that we're going to have to run and locally, or which we can push into a remote virtual machine, right? For running on a cloud system.
Just give me a minute. I guess my laptop is running up to battery.
Take your time.
So it will take a few minutes, maybe 5 minutes or so.
Okay, so this might be a good time. We usually take a mid-class break, right? So it's around 4:10. If you'd like, you can take a moment to stretch your legs and join us back around 4:15 or so. Is that okay? And then we will continue from there. Okay, I'll pause the recording in that time until such time that you guys are back. 4:15, right? 4 minutes, 5 minutes. Just as everybody's coming back, we're nearly done with the Docker build here, right? It's installing all the key packages that it needs, as well as those packages, dependencies, and and it's in this process of making this one container that encapsulates everything about our model and its dependencies. And there we go. It's done.
So
Right?
now we have successfully created a Docker image.
Mhm. And
So
so
it
if
is
you want
start.
to test it. Mhm.
Let's say I want to check my Docker image. For that, I use it as Docker images, and you see that we have just now created a Docker image, uh, the latest tag, and it just 25 seconds ago.
So basically, Vikas's machine has other Docker images on it, right? So it's showing up there. But then if you were doing this by yourselves, you would see only one, unless, of course, you deployed the same thing more than once, right? And it's possible to remove Docker images here as well, correct? But so Docker has a bunch of commands to establish the status of containers that are running and have been deployed and so on, right? So Docker RM, for example, will remove another Docker image that we don't need here, and it's going to delete that from wherever it is located.
This it didn't delete because the container is running.
Okay.
See the container running. So first of all, we need to stop this container, so that, or we need to delete this container first, and then we can delete this the Docker image. Deleting the container we can do.
So the Docker image becomes a container. Okay. So the code becomes a Docker image. The Docker image becomes a container. And the container is what's hosted. What and therefore exposes your API or app or whatever it is, right? Just like we have containerized in this case an API, you could containerize theoretically a Streamlit app if you like. You see? So that you can deploy that Streamlit app on any service, like in one example, Google App Engine or elsewhere, right?
So now I want to delete this Docker image. I'll do Docker RMI and my previous Docker image. So it has started. So see, we have
Yeah.
just now deleted. Yeah.
So basically, you don't need to memorize all these commands again, right? It's just that there is a whole world of commands, right, that allow you to understand what containers are running, what Docker images have been built on this machine, and so on. Okay, and Docker keeps track of these things, and it's all based on a command line interface. Oops, stop it.
Now we'll just try to run our the loan prediction, which is we have just built right now. So that we will use Docker run command, which is already there.
So the Docker run command identifies the internal port and the corresponding external port that needs to be exposed, right? And the name of the tag of your Docker image in order to spin that image up into a container that is going to expose your API or the contents of this, what the substance of whatever it is that you containerize. Yes. Okay. So let's go ahead. So this thing is simply exposing this outwards, and then it says, aha, there it is. So 172.17.0.2 is Vikas's external IP address, it so happens, right? And it's saying that that external IP address, :8118, as long as that, portable forwarding has been enabled by means of his router, and it's going through his firewall, will allow anybody in the world to access this API now on this machine, right?
So now, since we have run our Docker image, we can test this Docker image with our, with our tool Postman. Let's just do it right now. I'll just copy the endpoint here from here.
Loan prediction. So he's creating the endpoint, sorry, accessing the endpoint. Notice how he's creating a post command. The post command is what sends the request out, right? And then he's sending out the same payload that he previously had and going to check if the newly hosted container is able to respond to this request. So it's taking a while, it looks like. I think maybe because it's on your local host, you must need to put localhost :8118, but let's see. Yeah, could not send because I think the it's the external IP, right? So you need to, you're in your own network. So just put, yeah, 0.0.0.0, or you could put localhost, I guess, right? I'm not sure if you need a slash at the end of that too. So.
Correct. I mean,
And wasn't it loan underscore prediction? I'm not sure. Let's just verify that.
not sure.
Known dash prediction. Okay. There we go.
Yeah.
Mm-hmm. So in this particular case, that Docker container is hosted locally, so it's accessible at 0000 or localhost :8118, right?
Right.
Okay.
So you see, we can see here also that, yeah, it came here with a 200 success tag.
So 200 means success. That means it gave a successful message back, right? So it's logged that event in the command line, right?
So you're actually running a Docker image here.
Yeah.
You can verify that, yes, you're actually running a Docker image here, and with this, with this status.
Mm-hmm. So at this point, we created a Docker image, we converted it into a hosted container, we pinged the service that that container is exposing, right? At port 8118 in this particular case by design. A lot of things, right? Now, the only thing left to try is to put this container on the cloud, right? To see that we can manage to take this image and really run it anywhere rather than only on the local machine.
Now, one thing to notice here, I mean, if you see here, that I have just killed the run here. You see, I've just killed the run, but still I can use that API. See, you can still use that API because the container is running in the background. So if I do to check Dr. PS, Dr. PS -a, you see this container is still running. It didn't stop it. You see, it didn't stop it. So that's why our API is still running. Now, if I stop this container, let's say just to stop and the container name, the container ID. So we have stopped the container now. Now, if I check the API, you see it's not running. See, it could not send to the response. So that's how it works. To stop an API, we have to stop a container first. Container is something where our application is running. Okay. And that's how it works.
So Docker image becomes container, and container is what exposes a port to our API, right?
Yep.
Okay. Okay, cool. So, Vikas, to wrap up things for today, I was thinking maybe we could just take this and put it on Google Cloud, right? So Google Cloud, AWS, and Azure, on which is Microsoft Cloud, are all cloud services that allow you to deploy containerized applications to them. Okay, and in one example, we are familiar with Google Cloud, and there is a service called Cloud Run, right, which will allow you to deploy this container to the cloud. Okay, and just like we deployed the container using the Docker run command after building the container image, we can run this container on Google Cloud, so it's perpetually hosted using a certain approach, right?
Yeah.
So this is a fairly good slide to look into. Yeah. So you have your code that you have, right? The 4 files. We can put that into GitHub, and you're familiar with GitHub. Everybody has a GitHub account from all our previous lectures. We connect this GitHub account to a Google Cloud Platform instance, right? Which we have. I have a lab instance. And then we will host the code that builds out of the GitHub, right? Basically, not the code, but the image that builds out of the GitHub, into a container that is hosted on Google Cloud, and allow us, and that container will now be will allow us to send a new response, send a new request, sorry, a post command, and receive back a request, receive back a response. I'm sorry, right? We send a request and receive back a response. Okay.
Yeah.
So we can quickly go over just how that works out, I guess. But if it, yeah. Mhm.
Yeah. So this is just another, Cloud SDK shell, which we use for, I mean, you can use Windows terminal also, but for the sake of doing it in cloud, we can use this Cloud SDK, which is another tool or another terminal to push our Docker image. So let's say I check my uh, recently built image. There you see we have this load protection. And first of all, we need to host it into our cloud. We need to initialize our G-Cloud account. So for initializing, we do G-Cloud in it. So these are some series of steps we do to initialize our account and to authenticate our account in a GCP platform. I take my ID, I take my valid email address.
It's
And
the
the project.
yeah, that's the one, the first one. Mm-hmm. So we have a project named Medical Image Representation, which happens to be the one we're going to use for this academic exercise. But
Yeah.
So now G-Cloud Init has authorized us to now make a push to our project, right?
Yes.
So we've done the handshake.
And for pushing, first of all, we tag our image to the G Cloud credentials. For tagging, we do Docker tag our, our image and just tag it to bci.io slash our project ID slash our Docker image.
That's spelled incorrectly, but PREDI. It doesn't matter. It would just create a name. But yeah, so just quickly before you move on to the next line there. So here what we're doing is simply taking the locally built image, right? And then pushing it into what is known as the Google Cloud Registry, GCR, right? Where we're going to create within the project Medical Image Representation O1, which is the name of my project on Google Cloud, right? A new container called loan dash prediction. Okay. So let's go ahead and do that. You already did it, I said, I suppose, yeah.
Yeah, but I did it for previous Docker image. Let's just do it for the new one.
Okay. So we're giving it a tag so that it knows what to push, right? And then after that,
There
since
we
we have
have
a
the
new
tag.
tag there, yeah. And say Docker push, that's it. And Docker push is going to send this container, this image to the
container
Google
registry.
Cloud Registry, yeah. So basically taking the image, making it a container that sits on the Google Cloud Registry now. But now this can take a little while because it's 1.5 GB, right? Was the size of the container. You see, so it might take a while to kind of get there, right? But
So that's going before.
so
This
this
is
is
our
console.cloud.google.com, which is the Google Cloud Console. And we're in the medical image representation project. And we're going to check where we are in terms of the container that we're sending up, right? So for this, we go into the services. There are lots of different things you can do on Google Cloud. Go to the container registry, which is gcr.io, right? And then look at the images that are in there. So in this particular case, once our image is already sent up to the cloud, it's going to sit here and we'll see a new line here with the tag that we provided, right? So it's still doing its job. It's taking a while, but eventually it's going to make it up there, right? So because since this is going to take a little while, right, what we could do is let this progress. You could show us how the thing works for the previously uploaded container that is already up there, right? So we previously uploaded a container
so
for
once
learn that demo. Yeah. Mm-hmm.
this is a folder where inside it we have our Docker image which we have built previously for this particular problem statement. So there are a lot of services in cloud to deploy our application. Okay, so for that, we just go to Cloud Run, which is Google Managed Services. So I just create a service using Google. Let's call it as loan protection. So this is the main step here. We select the Docker image which we have just pushed to our container registry. In our case, this is Docker image. Let's just select it, and there we go. So we have just selected our Docker image, and now we want to deploy it in a cloud run. So for that, there's some series of steps we need to do. We just give a container port, give all, the rest of the things at default, keeping instances 10. That's it. We just took wait.
So there were quite a few screens involved, right? So once you had, so while this is happening, maybe because we can open up another tab and let's just go back to the container registry, right? So basically, from the container registry, let's just kind of just quickly revise the steps, right? So you went through all the steps, just quickly revise the steps without actually clicking into it and actually doing it this time, so we understand what's going on. So we started with the container image, right? And then, now you can see even loan prediction is up there, right? But we now want to take this container image, right, which is the Docker image, and convert it into something that's a hosted container, much like what we did locally. So in this particular case, go ahead. Yeah, what is the next step we did? We went into Cloud Run, right?
Cloud Run.
Yeah. And from here, we created a new service, right?
And
By,
yeah.
yeah.
So here we create a new service.
Mm-hmm.
Just give the new service name as loan prediction.
Yeah, so we can actually create many services from the same image as well. So here we're creating a second service. Eventually, we're going to delete this because it so happens that it costs money to do this sort of thing. But we'll close it in the end. But so all you have to do is give it a name and then configure the machine, the virtual machine that's going to create hold this container, right? Because you need to provision a computer in the cloud to be able to run the container from the image that you just uploaded, right? Yeah, go ahead, Vikas.
Now here in the next step, we just select our Docker image, which we have just pushed to our registry. So in our case, we have loan prediction. We'll just select this Docker image and give some additional.
And so right there, you see that it says continuously deploy new versions from a source repository. So if we, in this case, we have manually put the Docker image to the container registry, right? But instead, if we had a piece of code, right, that builds into an image, right, we could put that code in a GitHub repository, and this thing will pick up any changes that we make to the code and rebuild the Docker image and send it into the cloud application or as a container automatically, so that we always have our application up to date and on the cloud. You see? And that's something we're not demonstrating today, but you can do something like this, right? And that's one of the very interesting things about such deployments. And when you connect the code repository and make sure that any change in the repository reflects automatically in the build that is hosted, that's called continuously integrated and continuously deployed application development, right? So that means whatever the code is immediately reflects into a deployed application. And that is generally industry practice today. Yeah. Yeah, go ahead, Vikas. The last step was, I think, just putting the port number that you want to expose your app at, and in this case it was 8118. And you provision the kind of resource that you want, and that's it. And then you kind of make sure that you have firewall rules to make sure that the external machine is truly accessible.
And this is
And
just to authenticate that you're creating a public API. Yeah.
And that's it. And so basically, the one line that we did, which was Docker run, is now replaced by these steps that we did on the cloud, right? Because we're provisioning a machine on which the Docker run is happening behind the scenes, and we're calling that cloud run. That's all, right? And there are other services as well that will help you do CI/CD, just contain, which is going to allow you to bypass the step of building the image locally before pushing it to the cloud registry. So with that, if we go back to the list, right? So it's already up now. It's already up now. We have an endpoint there. See, so we can copy that and we can test that on Postman.
Yep. And even you can also try from your end also, because this will run
Yeah, this
anywhere
is
in
a
the
nice
internet.
way to, yes. So if you all want to download this thing called Postman, just go Google search Postman and you can download it. And you can send a post command here. So we're going to send some raw JSON, which corresponds to um, a request that we're sending to this hosted API, and it'll take a moment, contact the Google Cloud hosted instance, and come back with a response.
There
And
you
there
go.
we go.
Dr. Menon,
Yeah.
is there a limit on storage for Google Cloud? So like, for example, I've run web apps with Heroku app, but especially with, for example, machine learning programs, they're really dense and heavy in what they include.
Mm-hmm.
Do you have to like pay for extra cloud space? Or
Yeah, all of this is paid for, right? So basically, even what we just deployed will cost us some money right now, right? But Heroku is completely free, isn't it? And so there are some benefits to it. But in Google Cloud, generally speaking, if you recall, in one of the configuration steps that we went through with Cloud Run, there was this one cell which said, how much memory do you want to allocate to your machine? How much space do you need, and so on. You can actually determine those things and adjust them even later on so as to be able to make a virtual machine that holds this container that is truly um, going to have the chops to deal with the kind of traffic it receives, right? So you see on the bottom right, it says capacity, CPU allocated 1, memory allocated 512 megabytes, right? And request timeout 300 seconds. So it basically, if let's say that you don't have enough memory in your allocated machine on which you're putting this container, then you would increase your request timeout because you know it's going to take a while, right? But if you have enough um, uh, you know horsepower there, you can reduce the timeout so that you expect, because you expect the response to come back quickly. But all of this costs money, and generally speaking, you get charged per call, right? Per API call, and you get,
Okay.
yeah, that's how it works in most of these cloud hosted systems. Mhm.
And then also, can you use requests instead for API calls? Like, I know you guys are using Postman right now, but if I want to like submit images, right? Could I just submit that to request? That's kind of like built in, and then I can just get it from the array that it stores it in.
Oh, so basically you're saying if you wanted to use an API where you send an image, how you do that is, I mean, how we've done that before is we basically send a path, right? So let's say that there's this thing called Google Cloud Buckets, which is like a folder in your system, file system, right? You would have the images there, and then the API is passed a JSON that includes a field called, let's say, image path, which has the path to the image in the Google bucket. And as long as the Cloud Run hosted container is in the same project as the bucket, it will be able to pick up the image from there and work it. Generally speaking, people don't send images and such across with these APIs, right? You put it into a file system, and then that file system happens to be in the same project as your hosted VM and so on. And then you pass the path to that file system. That's how we do it usually in practice, right? So
Yeah.
the API itself has no payload. You see, the behind the scenes, the container is accessing the file in the right location and then going from there. But if you need to upload a file, then you need to have an upload portal which sends the file to the bucket, basically, or the file system, and then you provide the path to the file system so that the API is able to respond to it. You see?
Yeah, that's interesting. Thank you.
Mm-hmm. Well, because I will ask that, if we're all done, we can just kill the hosted APIs. But what we'll do is we'll keep one of them, the one that we were just testing. And if you could paste the URL and the sample JSON into the Zoom chat, right? Remember, you need to send it as raw JSON, and then that's the endpoint. You guys can try it out with Postman at your end. And what you would have done is you would have sent your very first RESTful API, access to your first RESTful API endpoint using Postman, basically, right? And we can delete the other two because to save billing, if that's all right. And has everybody been able to find the Postman website and download Postman? Raise your hand if you have. Virtual hand or real hand? Okay, some of you. Rahul got it. Rahul, Alex got it. Claire got it. Very good. So most of you got it, right? Um, would one of you volunteer to put the link to where you downloaded it from on the chat, please? And there's a platform specific one that you can access from your computer, and there's another one that you can access with a website as well, right? So it's a web-based Postman as well, yeah? And then Vikas is going to paste in the URL as well as the sample data, which you are going to send in as raw JSON, right? Basically, you need to select those options in the Postman. And then the first command is sent as a post command. Basically, you identify the URL with a post command. Yep. Thank you, Vikas, for patiently and painstakingly walking everyone through this. Very, very methodically prepared exercise. So everyone unmute your mic for 1 second. Everyone unmute your mic for 1 second. Let's thank Vikas for having spent time with us today. Let's give him a round of applause. This is very well presented.
Thank you.
Thank you.
Thank you.
So thank you, Vikas. Yeah, and we really appreciate this. And everybody learned a lot, I'm sure, right? And the video of this will be made available naturally on Canvas, but also I'll download a video file for you, Vikas, for your records. And I'm, at this point, right, this week we have learned how to work with tabular data, explore it, visualize it, build a model from it, export that model, make an API of that model, make a web app of that model, containerize and deploy an API and work with that containerized deployment either locally as well on the cloud. Now, I know today has been slightly unconventional relative to the previous lectures where we develop everything line by line. We will spend some time in the next 45 minutes or next 30 minutes, how much of a time it takes, to just quickly go over some of the artifacts that are key from our exercise that we've just completed, and so that you can attempt to do this by yourself, or potentially at least do it locally, right? At least do it locally. The cloud version does require you to have a Google Cloud account and a credit card and things like that, which is unnecessary for you all, but you know now how it can be done, right? At least building it locally and deploying your models locally would be itself a very interesting thing. And if you had a cloud hosted virtual machine, you can SSH into that machine and then deposit your stuff there and use the same commands, right? It's like running it locally at that point. Okay. So let's, give me a raised hand if you finished doing the Postman bit, everyone. Hannah, Larry, Catherine, are you guys done with the Postman bit? Claire had previously raised her hand, so I think she's done, right? Okay, so
You mean just installing it, or like
installing it, and then after that trying to send one post command with the properties that are provided in the chat here.
Do you want us to install it to our devices, or can we just use the web host?
The web one is fine also. Anything that, just so that you can make sure that you've officially made one post command and you've been able to get a response, right? Because Postman can be tricky because you need to have, you have to pay attention to all those little options to make sure that you're sending the right thing. Otherwise it won't respond correctly. And if you're having any trouble, guys, Veda, Rahul, anybody else, please share your screen and we'll help you out. Yeah. Theo, any trouble? You okay?
yeah, I'm just I just need to like make an account and stuff.
Mm-hmm. Okay. And then once you guys are done with that, I'll just briefly go over some of the artifacts that I'm going to put up in the drive, and then we could probably even call it a day, given it's a Friday evening. But I'm going to put some things up in there that will help you build your Docker file locally. Vikas, if you wouldn't mind, while I'm doing that, just putting in the commands that, the key Docker commands that you entered in the PowerShell, just as a list in the chat, then we'll just create that list here as well, and I'll upload that too.
Sure, I'll do that.
Mm-hmm. So we're going to put the model py file, the requirements.
Can we create a JSON file of the data, or can we just copy and paste the dictionary into?
Yeah, just copy and paste that JSON. It looks like a dictionary, I know, right? But just copy and paste that JSON into the little text box and it should be okay. You can also save it as a JSON and upload it if you're using the web interface, right? But yeah, just copy paste should work. Mhm.
Are you sure the URL is still up? It says that the request is not allowed or the method's not allowed.
Really? Because did you by
Can you share
accident?
it, please? Can you share your screen, please?
Yeah, let's share your screen, if you wouldn't mind.
Because we have to, in Postman, we have to.
So post command, no, not get, it's post. Yes. And you constructed the URL, is it? So the web interface looks kind of different. It constructed the URL. Is it port number? Mhm.
Is this the correct URL?
I think rather than going like putting this stuff in params, you have to put it in body and then switch it to raw. Like if you click off of the URL and go to body, I think that's where.
So let's do it. Yeah.
Raw, and then change the thing from text to JSON there on the right.
Yeah, text to JSON there.
Yeah.
And put the body out here, which we have sent in chat.
No. In the body, you need to paste in the yes.
There we go.
And then change the URL. Yeah.
Oh, it works. All right, perfect.
Yeah.
Yeah.
So before, what was it instead of body? Was it defaulting to params?
Yeah.
Okay.
It defaults to params. But I thought it would have worked regardless if you just, because I feel like body is just like a raw text, right? Like it's just an abstracted JSON file, what this is, right?
Yeah, I know how did you construct that URL, or did it construct the URL for you?
The URL as in what was
On
in
the top, right?
It
Next to the
constructed it automatically.
It constructed automatically. So in the web interface, it constructs the whole thing on the
It
top.
happened to me too on the app, like the desktop app. I think it's anything you put in params, it puts in the URL.
I see. Okay, well, I mean, it seems like this is working out with only raw JSON sent in the body.
I don't know why. It's weird.
Yeah, it's a little weird, but there might be a way. There might be something quirky about how we need to send it.
Perfect. Well,
Thanks.
sorry for the bother. Thank you.
Hey, no, thanks. I mean, I'm glad we could find out that little quirk there. Okay. Anybody want any assistance with regard to this for now? And the Docker commands are coming our way just so that you can do the build and this and that. There'll be a video for this class too, naturally. And so it'll be on the video, which I encourage you to watch, right? If you wanted to redo anything. And all the code, including Docker file, loan prediction, .py, loan prediction IPYNB, and the model pickle and the requirements are all on your Google Drive, right? So you should be able to see all that content there. So you can try things out. The only thing that you need is now the commands for the Docker, which are coming your way from the chat right now. And, remember, you first need to build the Docker image from the Docker file and the requirements file, given the py file that exposes your API or the py file that opens your app or whatever it is. And then you deploy the Docker image, right?
Yep.
As a container. That's the idea. Really, that's it. And then there were some other interesting commands that were like docker ps-oa and things like that. If you could add those as well, because basically those are useful for the purpose of diagnosing which images have been built, which containers are currently running, and then how to delete a container. And all of those things are part of the video, but if you wouldn't mind just enter them here, and we have that command history, so to speak, which we can add to the record, right? But that is basically what we have for today. Any questions about what we saw today and learned about today? Now, there's no substitute to doing, right? you should at least try to do some of these things, but by yourself. This being said, the video and watching how this works, understanding it on a flow diagram basis, right? I mean, like or as a flow chart or flow as a process is also going to be of value, right? What is the command for deleting, Vikas?
Yes, I'm sending it.
Docker delete, right? And then you delete the container. There we go. There we go. Okay. So next class, what we are going to do is we are going to try and advance our knowledge to attempting to do things with images. And so Tuesday we'll learn about, you know, how to build models with images and this and that. Okay, and then after that we will have another one of my colleagues and students work, you know, show us another demo of how they do this on a very sensible level with a very interesting application. So we'll use, yes, convolutional neural networks and other things. But actually, you know, since we have 30 minutes, I wanted to tell you all about one little thing. There are lots of these auto ML tools out there, including ones on Google Cloud. Okay. And these will help you build models from tabular data. But amongst the various ones that I've seen, there is this one really nice one called MindsDB that if you haven't seen, you should check out. And I will show you how it works briefly. Okay, and we can use it on the loan prediction data set as well. And maybe I'll show you how that works in a moment. But basically, these solutions are used for being able to make models without any prior knowledge, pretty much, right? Just based on some prior data set and a graphical workflow. There are lots of auto ML tools that will generate tons and tons of models, starting with a tabular data, right? MindsDB is one of them, right? And so if we went into, if you wanted to know what MindsDB is, right? I mean, you can just go to this website. I'm just going to share with you, and you can download a free version of MindsDB, right? Okay, so once you have the MindsDB dataset, the application, right? The next thing is to be able to run it, right? And I have a version of the MindsDB installation locally, which is maybe a slightly dated version, right? But it allows you to bring up a graphical interface for the purpose of modeling tabular data, okay? And so I'm just starting that up, and let me just share my screen. So MindsDB is this application, right, which allows you to have a graph for the purpose of modeling data, right? Okay, and you see that it has a computer.
Professor Menon, I think you're muted.
Oh, okay. Did you guys lose me for a second, and did you lose my screen?
Yes
Yeah.
and yes.
Oh, okay, okay. Let me start again. So I guess I just have too much stuff going on this computer, but this MindsDB thing will install as an end user application, and it will, if you double click it, it kind of opens this web application, right? Which looks like this, okay? And so here, you know, you can just upload a data set and, you know, do things from there, right? So in one example, right, you could import a data set, let's say from a URL or from a file or by uploading. So let's say I wanted to upload a file. And in this particular case, I want to upload in this example, the lone data set, or we can even take a smaller example just so that, because my computer is running out of memory here. So basically I'm going to call this the British seatbelt study, right? Okay, I'm going to upload this data set in here, and it will parse it and allow us to preview the data graphically, right? And then once we're done, we can actually even examine the quality of the data. It's going to analyze it in some way and tell me about whether this data set has good data or bad data. And it'll give me some sense for, the driver skill, does a distribution, and it provides a histogram of this based on bins. And it says the most number of driver skills in this data set was about, was seen in the range, most number of occurrences was for driver skill between 112 and 115 or so. And then, it says the law column is available as 0 or 1, and it's a binary categorical. It identified that correctly with very few ones. 12% of them are ones, 88% are 0. So it gives you this descriptive analysis nicely. And then after that, I can train a predictor based on the British seatbelt study, and I can call this predictor Go Brits, whatever, right? And I can say, I want to predict in this case, whether the law for seat belts was in effect or not, which is a binary outcome. Now I hit train. Now in this particular case, it's actually using all the columns in the data to predict this response, right? Rather than, only the selected 2 columns that we learned of last time, right? But, you can see that it gave me an error. So I'm just going to delete that and then, fix that up. So basically, there is seatbelt study, and there is an advanced mode where you can say select study the columns to be removed, and we'll say we'll remove all of these. So we only want to use drivers killed, so on, and just keep the columns that we want. And we want to predict the law column, right? And then, is it a time series data prediction? I mean, it can even do time series modeling, but we're not. So in my case, I have a GPU on this machine, and here you can, say run for at most 1 minute, or let's say 2 minutes, and don't run more than that. You can actually time your stuff. And then once you're done, right, you can hit train, but it's not letting me hit train. What do I, give a name for the predictor. Let's call it GoBrits1 and hit train, right? So it's going to train a model to predict this response. Now, it doesn't train one model, it trains a lot of different types of models that are relevant to this binary classification problem. And then it will, come back with a result, right? So it's taking some time to do that only because it's predicting from so many different models, right? It's making a model for this binary classification problem from lots of different models. And then it's going to expose, it's going to reveal those models here, out here. So it says it was able to make a model that had an accuracy of 1, that means 100%. And now if I preview this model, it said that it took a random 143 for training and 36 for testing, right? And it got 100% accuracy for this very specific combination. It's not done cross-validation or anything, but it took some specific training set and some specific testing set, and it got this 100% classification. And then it said that driver skill was more important than van skill in terms of relative variable importance for prediction from this model. And can I trust this model? It comes up with a confusion matrix, much like we've done before. And it says the predicted and actuals are, very, very correlated, right? And so from that perspective, it kind of built a model, diagnosed it for me, and then, even allows me to download this model, it so happens, or even query this model for new data. So query means test it for new data, right? Just like we made that Streamlit app for. So here we say, let's say van skill is 1, driver skill is 10, right? And then run query, and it's going to send this prediction through and come back with a prediction saying that I'm 97% confident that the prediction is one, that the law was in effect. See, this is pretty much what our Streamlit app did the last time, correct? Everybody remember this? Yeah. And so that's it, right? So basically, this is, there are several automatic model builders out there for the purpose of building data from tabular models. There are also automatic model builders out there for building models from images, and we'll go through that when the time comes. But you can actually download this model as well, and such. But in some versions of MindsDB, but I'm not sure if that was their original intent in this particular app. Maybe they wanted to buy something, I'm not sure, but I thought this was a very nice looking interface that you guys could try at home by yourselves, right? In order to try to build models by yourself, right? It's called MindsDB, right? Pretty cool, right? The only thing is that it doesn't allow you to export it into a neutral file and that sort of thing, which is unfortunate, right? Because that's the kind of relevant stuff that you need in order to do something with this, right? So this just tabular data need not always be in CSVs. You can probably have a connection to a database which queries the data and brings it into your area and so on. And so this thing has some connectors for that sort of database-based pull and so on, right? Any questions about MindsDB for the moment? Right. So the reason I shared with this with you all is just so that you are aware of the possibilities of doing things using automatic ML tools which are present, right? And next time, to wrap up the tabular stuff, I will cover two topics in tabular modeling. One is H2O, right? How to use H2O. So we're going to cover H2O.ai. Then we're going to cover auto ML tools, right? In general, and then ensemble models. These are the things that we'll cover in terms of tabular data. And then after that, we will get right into working with image data, and we'll talk about image models and auto AI, right? I mean, auto ML, correct? So these are the things that we'll cover next class. And so that should be pretty exciting. So we'll spend about half the class in the first class, talking about auto AI models and that sort of thing. I'll also show you how to connect your data to Google, connect to Google Sheet, for example. I mean, did I show you all how to connect to Google Sheet in the first class? Yes, I did, right? Yeah, but we'll do a little exercise where we'll crowdsource some data from Google Sheets. It'll be pretty interesting. Either next class or the following, and build a model from there and so on. And we'll try to distinguish between linear and nonlinear models, and do some theory, right? Linear versus nonlinear models, right? Now that we have a sense for what machine learning does, and then typical model performance metrics, right? Sensitivity, specificity, precision, and so on, just more formally visited, so that you have that theoretical knowledge as well. Okay, so these are the concepts that we will try to cover next time. Okay, I think for today, since we didn't really have the 15-minute break, it's probably a good idea to wrap it up. I think we had more than enough fantastic content. Hope you found it inspiring and interesting. Please try this at home, right? Unlike your typical warnings where you don't want people to try things at home, this is one of those things we want you to try at home, right? So please try this at home, and let me know if you have any questions. We're always available to answer questions and help you out as needed. Okay. So with that, have a good weekend, everyone, and we will see each other next week.
Thank you.
Have a good weekend.
Thank you so much, Dr. Menon.
Thank you, Dr. Menon.
Bye.
Thanks a lot.
Okay, Vikas, thank you so much. I think this is fantastic.
Yeah.
Let me stop the recording.